This term we call the permittivity. It just measures the resistance that a material has to an electric field. And if we allow the material to be just free space, then kappa is 1, and the permittivity is equal to epsilon naught, so we call epsilon naught the permittivity of free space.
Thanks for watching. If you enjoyed this video, please hit the subscribe button and ring the notification bell so you never miss an update. Leave a comment below to help grow the channel, and don't forget to smash the like button.
Dielectrics, lecture 104. Let's first talk about the word dielectrics, right? The die part really comes from dia, D-I-A, which I think is Greek. It means passing through. And electrics, it's electric field, right? So these are materials that allow the electric field to pass through, okay? Unlike, say, metals, you have electrons that can move around and completely counteract the electric field inside of the substance, right, negating it. Dielectrics do not have free charges, and so sometimes we can just call them insulators. So you'll recall that if I have an electric field, let's say in this direction here, and I place an otherwise neutral atom or molecule in that electric field, then what ends up happening is you get a polarization where the positive charge and the negative charge separate out just a little bit, right? So we're going to look at the consequences of this in regards to, we're going to look at the consequences of this when we put a dielectric material in between the plates of a parallel plate capacitor. So let me see if I can draw that. Okay, to start with, remember, a parallel plate capacitor is made up of two parallel plates separated by some distance. We don't need to worry about the distance. We could call it A right now, the separation distance. And we apply a potential across it, right? So the electric field is going in this direction. Did I draw the electric field in the right direction? Give me a second. No, I don't think I did. No. All right, and so you'll recall that the electric field, right, which I can just write over here if you need me to, is the charge density over epsilon naught, right? But I'm going to distinguish this. I'm going to write sigma sub F for free, okay? I also wrote E sub F for the electric field due to the free charges, right? So I put this parallel plate capacitor in here. I've applied a potential difference across the plates by maybe hooking up a battery or something like that, right? And so we get an accumulation of positive charges on the plate nearest the high potential and an accumulation of negative charges near the plate at the lower potential, okay? Which I've defined as 0 in this case, right? Because remember, all that matters is the difference in the two, okay? So delta V is basically V. Now, the question is, what happens if I put a dielectric material in between here? Like if I took a slab of glass and inserted it between the plates of the capacitor? I'm going to assume that I fill the volume inside here, okay? So that it's not like a slab with a lot of distance between it. It totally fills this. The thickness of the slab and the spacing of the capacitor plates are the same, okay? And if I do that, what's going to happen, right, is the electric field, and I'm going to draw maybe the molecules in red, and I'll do it like this, right? Look at the diagram over here to guide you, right? So we're going to get an accumulation of positive, I hope this shows up well in the video on the camera. Okay, now I've exaggerated the detail to which the molecules are polarized. In reality, the separation is never all that great. But if we think of this material, right, we can see that there's a bit of a displacement of negative charge. So the negative we call them bound charges, okay? So near the positive plate, you have a collection, an assembly of negative bound charges from the polarized molecules, right? Because the negative plate is on this side, right? And on the negative plate, we have an accumulation of positive bound charges. And so you can think of, well, what does the electric field look like for this? Well, it starts at the positive and it goes to the negative. So here we have an electric field which is kind of in the opposite direction. I'll only draw one field line per little section here. And this we would call E sub B for bound, okay? I messed up my E sub F over here. E sub F for free. All right, and so you can see that the electric field is actually, for the whole capacitor, right, is attenuated, okay? Because we've got one electric field from the free charges headed in this direction, and it's going to superpose with the electric field from the bound charges in the opposite direction. So we can write something like E is now equal to E sub free minus E sub bound. So since the electric field is reduced, now let me just ask you a question. Does it make sense that the electric field from the bound charges is less than the electric field from the free charges? Because remember, these are induced electric fields, right? The polarization in the molecules is induced by the presence of the electric field from the free charges, right? Yeah. So it seems reasonable to expect that the electric field that we see when we put the dielectric in here is proportional to the free charge electric field over some factor, right? So it's attenuated where this kappa is greater than 1, greater than or equal to 1, okay? So if we have no dielectric material in there, it would be equal to 1, and then the electric field between the capacitor plates is just the free charge electric field divided by 1, right? Yeah. But if we put a dielectric in there, now it's reduced, right? So kappa can be greater than 1, causing the electric field to attenuate, right? Yeah. So if I write this a little differently, if I write that E is equal to E sub F minus E sub B, which is equal to this E sub F over kappa, and I solve for E sub B, so what is the bound charge electric field? I'll move over there, this will move over here. We'll get E sub F times 1 over kappa. So I just solve for the bound charge electric field. And so this basically says that it's equal to the free charge electric field minus some amount, right? So as long as if kappa is equal to 1, the bound charge electric field is just equal to 1 minus 1. The free electric field times 1 minus 1, which is 0, right? So if kappa is 1, we have no bound charge electric field, right? Does that make sense? So what is this kappa that I wrote over here? Well, we call this the dielectric constant. Dielectric constant. And so different materials, being made of different molecules, have different dielectric constants. Some molecules are easier to polarize than others. Some have a permanent polarization. So you don't even need to apply an electric field. It's already polarized, okay? And if you stick it in between the plates of a parallel plate capacitor, it will maybe increase the polarization a little bit, but usually the induced polarization is much less than the permanent polarization that a molecule might have. Okay, and I think maybe next week we'll talk a little bit about things like this, since the research that I did as a student was involving ferroelectric materials, which have very large permanent dipole moments, and so we'll talk a little bit about that, maybe in the context of something like lithium niobate or lithium tantalate or barium titanate, some of these molecules that have large permanent polarizations. Okay, so let's just remember, using this formula here, that the electric field is equal to the charge density, the surface charge density divided by epsilon naught for a parallel plate capacitor, right? I can substitute in for these two terms here. E sub B, we could think of it as, let's write another equation over here. E sub F, so this is the electric field due to free charges. We could also write something like this. E sub B is equal to sigma sub B over epsilon naught. So that's the charge density of bound charges, right? And so if I substitute in for this, we can see we would get sigma sub B equals 1 minus 1 over kappa times sigma sub F, okay? So you see how the bound charge density and the free charge density are related. And recall that in this scenario, the electric potential, or voltage, is equal to the electric field times, I'm going to use A because I said the distance here was A, right? Well, I can write this as E sub the free charge over this dielectric constant. So that would give me E sub F over K, or kappa, times A. So we see that the electric potential also is reduced for a dielectric, right? So in the homework, I'll give you a variety of problems in which we hook batteries up to capacitors, insert dielectrics. Maybe we disconnect the leads of the battery before we insert the dielectric, or we leave them connected, and so various circumstances to see what changes in there, okay, how the potential changes, how the charge density changes, and how the capacitance would change. That's what I'm trying to get to here. is let's write down the capacitance, because remember that the capacitance, C, is the charge divided by the potential. And so if I write this as the free charge dividing by the potential, right, we see that we get the kappa is in the numerator this time. So this is kind of the point behind these dielectric materials, is they increase the capacitance, right? That's the number of the charges in coulombs per volt of electric potential, right? So we can actually increase the capacitance of a capacitor by inserting these dielectric materials. Because when I divide the charge by the potential, right, and write it in terms of the free charge, right, then we introduce E sub F over kappa times A in the denominator, which now puts kappa in the numerator, you see? And we'll probably see this again in a minute. But first let me summarize the stuff that we have so far over here. Over here on the board, I've written a summary of the electric field, the potential, the capacitance, and the charge density, and how the dielectric constant affects that. These will be very handy in solving your homework problems, okay? You'll have to think carefully through them, thinking about what changes and what does not change, and okay? So you'll want to have this as a reference. I want to think about the polarization in the dielectric material a little bit more closely, and I want to think of it like this. So when I have a slab of material, right, and it becomes polarized, what's really happening here? So I'm first going to draw. This is what the little slab would look like if it was not polarized, okay? Once I polarize it, though, right, I'm separating out the positive charges and the negative charges just a little bit. And so you can think of it as like another plate. Which I'm going to draw like this. So the dotted line plate is like, think of it behind, and now I stretch them out. I wanted to get a couple of transparencies and put the positive charges right on top of the negative charges and then slide them apart a little bit, and then you'd physically see what this looks like. So the negative charges will be down here, let's say, and the positive charges will be up here. Okay? And so you can imagine that if I were to slide these two sheets back together, right, the negative charges will be on top of the positive charges on the top sheet. Does that make sense? And then here we would have negative charges all along here. I hope it's a good illustration. I don't know. All right? And so when we thought about the individual dipole, right, we talked about the individual polarization, we thought of a dipole as just a single molecule being stretched apart a little bit, such that the center of positive charge and the center of negative charge was a little separated, right, by some amount. We'll call it D, okay? And so in the molecular picture, we had a single molecule. We could write a little p. The dipole moment, right, was equal to the charge being separated. Remember, we just write Q because we have one positive charge, one negative charge being separated, for example, okay? If you add the charges up, obviously you get 0, okay? Yeah. So you think of how much positive charge is separated, or you can think of how much negative charge is separated, and you write just one term for the charge. Times D. So that's our little polarization for a single dipole. Now what about for a slab, right? Well, in this case, I want to think of a different term. I'm going to write a big P, and so from here forward, when I write a big P, I'm talking about this scenario and not this one anymore, with the possible exception of next week if I talk about polarizability inside of materials, I may talk about molecular polarizability again, but I'll mention that. But in general, so this is like the dipole moment per unit volume, okay, because this is a slab of material, and so we're imagining that there are some number n dipoles per unit volume, right? So if you have 1 per cubic meter, that's 1 dipole per cubic meter, or you have 10 to the 23 per cubic meter, or something like that. It's some number density of dipoles, times the charge on each dipole, and times this distance d, which is the same as this distance d here, right? It's the net stretching. So whenever I stretch them out, the whole sheet just kind of gets, it's like it's slided over just a little bit by the same amount that each dipole is slid over, right? So this is now my dipole moment per unit volume. This has polarization per unit volume. It's a dipole moment per unit volume, okay? This is the number of dipoles per unit volume. This is the little p, right? The dipole moment of each of the dipoles. And so this makes this a dipole moment per unit volume. Now if I wanted to calculate, well, what is the charge density on each of these surfaces, right, from the bound charges only, right? How would I go about doing that? Well, first thing I would do is I would say, well, how much bound charge do I have? Well, I could take the dipole density, right, that's the dipole number of dipoles per unit volume, multiply that times the surface area of this surface or this surface, right? Because remember, this is a slab. I've just drawn a cross-section of it, right? But in reality, this is a slab of material, and it'll have some area, right? So you can think of it as, this is the slab we're talking about. We're just looking at the cross-section of it. But if we look at like this, we see there's some surface area here. And I want to know how much charge is on this surface area, but bound charge, right? This is not the free charges that we talked about before with the capacitor. These are bound charges. So I take the dipole density times the area, but this, we need a volume, right? So the volume is just this little distance d times the surface area, right? And this is the charges. Now if I divide out area on both sides, this charge density turns into, this charge turns into a charge density. And I forgot to put Q in here, times Q, right? Times Q. And if you look at this and you look at this, it's like, well, that's crazy because these are the same thing. So it would seem that the polarization, or the dipole moment per unit volume, is equal to the surface charge density of the bound charges. Okay? So I remember being confused about this when I was a student, because it seems kind of weird, right, that these two things are the same thing. But if you like look at the units of this, right, it kind of makes sense. If I've got something that has units of, dipole moment per volume, right, where volume, of course, is meters cubed, right, so write that in meters cubed. Dipole moment is, some number of coulombs times a distance in meters divided by the volume again. The meters cancel, and this just ends up becoming coulombs per meter squared, which are the units of charge density. So the units of dipole moment per unit volume is the same as charge per unit area. Okay? It's a little weird, but it is what it is. If I were to put my capacitor plates back in here again, this is where my positive charges are, free charges, negative free charges. The potential V is here. This is potential 0. And I were to do Gauss's law on this, right? And so I could draw another Gaussian surface in here, like this. Then Gauss's law tells that E times A is going to be equal to the free charge, which we get on the plate in the metal, minus the bound charge divided by epsilon naught. If I divide out the area, then I get that the electric field is equal to sigma sub F minus sigma sub B. That's the free charge density minus the bound charge density. And if sometimes I'm writing the bound charge density with an uppercase B and sometimes with a lowercase b. Ignore, they're the same. Using this relationship here, though, the bound charge density is just the polarization, right? So I can replace sigma sub B with the polarization. At this point, we have to talk about, well, what is this polarization, right? And we're going to talk about it. Remember that if I don't have the electric field present, right, then there's no polarization unless we're talking about things with permanent dipole moments. But let's ignore that for a moment. This polarization we can write in terms of a new concept. This is a chi, the Greek letter chi. I draw terrible chi, so I apologize for that. This new term we get, we call it the susceptibility. And so the susceptibility is a measure of how much does a given material get polarized by an electric field, okay? So you can see it must be related to the dielectric constant, right? Because the dielectric constant was kind of telling us what's the increase in capacitance, right? Because of a dielectric material. And that was related to the polarization that was induced in the material, right? Yeah. Which is decreasing the electric field in between the plates of the capacitor. And this, right, is supposed to be a measure of how easy it is to create a dipole moment in a material. Now in general, here I've shown it to be linearly proportional, okay? And like the whole field of nonlinear optics is all about basically starting with this equation, but considering nonlinear electric fields. And so you get an expansion of terms, right? You get a susceptibility that is expanded in terms of E and E squared and E cubed and E to the fourth, right? Usually E squared and E cubed are kind of the most common applications in nonlinear optics. but that's when the electric fields are really high, right? There's a response which is different than it is at low electric fields. So here, though, we're going to consider it to be linear. If I insert this in here, I can replace, well, I guess I could just write it, sigma sub f minus epsilon naught chi times E divided by epsilon naught. Let me just write this over here because I want the room here. So I'm going to put these two electric fields together because on the left-hand side I have the electric field, on the right-hand side I have the electric field, right? So let's put them together. We'll get E times, well, I multiply everything by epsilon naught. Oh, goodness. Let's see. I'll just do the algebra here, and then we might overwrite some things. Epsilon naught E plus epsilon naught chi times E is going to equal sigma sub f. I can factor out the epsilon naught, put it over here, right? Factor out the E, put it right here, and then I'm going to move this over here, 1 plus chi, basically just dividing that out. That gives me the electric field is equal to this. And if we look back over here at this equation, right, specifically here, right, sigma sub f, that's the free charge density, over epsilon naught times the 1 over kappa, right? So this seems to imply that our dielectric constant kappa is equal to 1 plus chi, the susceptibility. So now we've related the dielectric constant to the electric susceptibility. We suspected there was a relationship, right, because they're kind of the same thing. And so now we have that relationship here. So the dielectric constant, which relates how much the electric field is reduced by the presence of a dielectric material, is related to the electric susceptibility, which relates how easy it is to induce a dipole in a material. Okay, I don't remember what lecture it was. It was a recent lecture, though, when we talked about Gauss's law. And if you look back at that lecture, what we did for free charge, relating it to the divergence, we can also do that for bound charge. And if we do, it can be shown that the bound charge density is equal to the divergence of this new vector, the polarization. Okay? I haven't been writing the hats on. I should be writing a vector bar on this because the polarization really is a vector. It's got a direction. That's the direction it's being stretched, right? And so recall that del dot E, E is a vector, is equal to rho over epsilon naught. This is the divergence that we got for the electric field. I can write this as rho free, just rho sub f for rho free, plus rho bound. Rho in this case is the total charge density, so we have the free charge density, that's the charges on the plates of the capacitor, plus the bound charge density, that's the charge density that we got from in the dielectric material itself, right? So rho is just the sum of these two, but remember, I said that we can show that that the bound charge density is related to the divergence of the polarization. I have two divergences, right? Remember, the divergences are a dot product, okay, with this basically derivative operator, right? It's a derivative operator, it's a vector, right? It's the derivative with respect to x. It also has a y component, derivative with respect to y, and a derivative with respect to z component, right? So let me pull these two near each other so we can write that del dot epsilon naught E plus del dot polarization, right, is equal to rho f, the free charge density. Now I can factor out the del in here, and I'll write like this. This can be just equal to this, epsilon naught E plus P. So through the distributive property, we can distribute this derivative, okay? And that will be equal to rho f. This term right here, for historical reasons, so that we could always just deal with the free charge density, and we didn't have to worry about the bound charge density, because originally it wasn't even well understood about this bound charge density. But now it's just a matter of convenience, so that we can just deal with the free charge density, right? We can redefine a new term. I know we're giving you so many terms, right? The polarization, and now you get a new thing. And that's right here. If we call this piece right here, we call it D, the displacement field. It's, again, another vector. People think of it like electric field. Then we can write Maxwell's first equation like this. So compare that with this. Well, again, these are all vectors. Okay? So del dot E is equal to rho over epsilon naught. Del dot D is equal to rho F, the free charge density. Okay? So here you don't have to worry about any bound charges at all. We kind of build it into this new field D. Does that make sense? So, and there's no other good reason to do it other than to say the stuff in this term right here, right, by moving the bound charge density all together with the divergence of the electric field, right, we can write things in terms explicitly of the free charge density without having to worry about the bound charge density. Okay? And so Maxwell's first equation gets replaced with this. And so if you ever look at the traditional differential forms of Maxwell's equations, usually this is the first one instead of this. Okay? And this D, let's see, we can do a little bit more with this D. D is equal to epsilon naught E plus P, the polarization, right? Well, if I use this here, this just becomes epsilon naught chi E. Yes? Yeah. I can factor out the epsilon naught and the E, and I get 1 plus chi. Actually, I'll put the E over here. This. And recall that 1 plus chi is just the dielectric constant, kappa. By the way, kappa, so we don't get confused with the Coulomb constant, right? Big K, which is 9 times 10 to the 9th newtons per Coulomb squared per meter squared, right? Meter squared per Coulomb squared. It's not the same. This is a kappa, not a K, okay? So the dielectric constant, it's a unitless quantity. So I just replace 1 plus chi with the dielectric constant. And in general, we define yet another new quantity, epsilon, which we call the permittivity. So the permittivity measures how much resistance you have to the electric field, right, in a given material. So it's how much it resists the electric field, hence the term permittivity, right? And so this is the permittivity. Epsilon is just equal to epsilon naught times kappa, right? We just replace this with this. And there's a couple of ways to think about this. So now you can understand the origin of epsilon naught, which we call the permittivity of free space. Okay, so in free space, kappa is 1. And so the permittivity is now equal to epsilon naught, this constant we've been dragging around, right? I can write over here that the big K, the Coulomb constant, is equal to 1 over 4 pi epsilon naught, right? So big K is the one we use in the force law, right? Coulomb's law. And when we talked about capacitance, we wanted to introduce epsilon naught because of the farads, right? And we call it the permittivity of free space, and the reason why is because of this, okay? This term we call the permittivity. It just measures the resistance that a material has to an electric field. And if we allow the material to be just free space, then kappa is 1, and the permittivity is equal to epsilon naught, so we call epsilon naught the permittivity of free space. If we just looked at it like this of course is also equal to epsilon naught times 1 plus chi. Okay, and in free space, there is no polarizability. You can't polarize it, so the electric susceptibility is 0. Okay, and so again, we get that the permittivity is equal to just epsilon naught, so we call it the permittivity of free space. And so now you understand why it's named thusly. I think that's all I have for you, okay? The homework will not be nearly as complicated as some of the stuff I showed here. I just wanted to set the stage so that we can use some of these things in upcoming lectures. I don't think I have anything else to add to it. But I mean, you're going to see D, right, in books and anywhere else in the future. So I wanted to make sure that we understood where that came from. It's just a convenience so that you can talk about Maxwell's equations and divergences in terms of just the free charge density, and you don't have to worry about calculating things for the bound charge density. And also relating this mysterious permittivity of free space, which is often misunderstood, but why we call it the permittivity of free space, and this is why. I think that's it. Any questions? No? Oh, that's a nice face. How about you?
No.
Okay, that's it. Where's my clicker?